Welcome to Module 9 from our series on artificial intelligence. This module provides a brief review of gradient descent as applied to machine learning. This module will teach us about gradient descent and serve as preparation for the next module on supervised machine learning. I'd like to begin with a question and ask how we can optimize a more nonlinear or a highly nonlinear objective function like the one shown here, natural log of 1 minus x, etc., etc. You may recognize this function. We took it from an example in the last module. Now, there are several answers to this question, but we're going to focus on gradient descent as one potential way to optimize these types of more nonlinear or highly nonlinear objective functions. Although we often cannot solve directly for the minimum or maximum of a nonlinear function, we may search for critical points by performing 2 or 3 steps in repetition. The first of which is to select a starting point or an initial condition for a search. Now let's imagine that we're standing on a hill and we want to find the bottom of the hill, the lowest point. How would we do that? One thing we might do is take a look around us, evaluate the slopes locally around this point, and that might tell us in which direction we need to begin walking. Now, with regard to a mathematical implementation, fortunately, we know that these slopes, this gradient, is relatively easy, relatively straightforward to compute. Now, once we've evaluated the slopes, evaluated the gradient, we would take a step in the direction of the steepest downward slope. For minimization, at least, if we're talking about maximization, then we would take a step in the direction of the steepest upward slope. We would then repeat these last 2 steps until we reach a point at which no slope leads further downward. All the slopes are either flat or ascending. And this approach that we just described forms the foundation of the gradient descent method. Consequently, gradient descent may be used to minimize, maximize, or optimize the output of a nonlinear function. It may also be used to solve nonlinear equalities like g of x equals 0, assuming that g of x is nonlinear. This requires us to employ an objective function like g of x squared, for example, where the minimum value is 0 and is not allowed to go negative. Gradient descent, as we demonstrated on the previous slide, is an iterative algorithm, one that employs first-order gradients or linearized tangent approximations of a nonlinear function to migrate or move from an initial starting point to a local minimum or maximum. Now, note that this local minimum or maximum may also be global, but it's not guaranteed to be. Gradient descent may be applied to both constrained and unconstrained optimization problems. Now, in this module, we're going to focus on the unconstrained case. However, constrained optimization problems are addressed in several other lectures that I've published, specifically on the method of Lagrange multipliers. And on my YouTube channel, you'll see there's actually a playlist specifically for that topic. So let's revisit the example of a highly nonlinear optimization problem from the previous module. Like we did in that module, we first need to define our optimization problem. We want to minimize an objective function with respect to x. It's defined as natural log of 1 minus x1 plus x1 cubed, etc. Again, like we did in the last module, we calculate the first order gradient of the objective function with respect to x. You can see that array right here. Now, one thing that we didn't do in the last module was show how to solve. Now, assuming we want to use gradient descent for this purpose, we need to define an iterative update expression like the one shown here. So let's take a closer look at the gradient descent update expression. We'll go through it piece by piece. Here we have x. This is the variable that we want to optimize. It has a parentheses superscript it equals 0. So this is telling us it's the x value for the 0th iteration. It's the initial condition. Over here, we have x, again, the variable we want to optimize, with a superscript of it plus 1, so this would be the updated value, the value of x for the next iteration. Here we have the alpha coefficient. We'll talk more about this in a second. And then we have our gradient, which is the derivative of the objective function with respect to x evaluated at the initial condition. This operator right here will be a minus for minimization and a plus for maximization. So how do we use this expression? Let's take a look. The first step would be to define the initial condition or starting point. And if this is not the first iteration, then this essentially could be it equals 1, and this would be it equals 2. So this expression works for more than just that initial iteration. The second step would be to calculate the gradient or the slopes at that point, again using our current location or our current x value. We then scale the magnitude of our update or scale our step size, and then finally execute the update or step to generate a new x value, a new location. So essentially, the new location, the new x value, is equal to the old location minus the product of 2 elements. We have the gradient, which tells us in which direction we should be moving, and then the alpha coefficient, which tells us how large of a stride that we'll be taking. Now, ideally, for minimization, if we apply the objective function to the updated value, it should yield a number less than if we applied the objective value to the previous x value. Now that we better understand the update expression, we can apply gradient descent to our highly nonlinear example, and we'll go through this step by step. The first thing that we'll do is initialize our x variables. We see that the initial condition of x1 is -1, and the initial condition of x2 is +1. Note again that the parentheses superscript tells us the iteration number, the bracketed superscript tells us which variable it is, so x1 or x2. We're also employing an update coefficient, an alpha value of 0.1. Now from this point forward, we're entering our loop, right? We need to repeat steps 2, 3, and 4 as many times as required to reach convergence. Step 2 within the loop is to calculate the gradient. We should already have a closed form expression for it, so perhaps we could better say evaluate the gradient. So we take the value of -1, plug it in as needed. We take the value of +1, plug it in as needed, and it generates a gradient of -1.5 and +5.0. Step number 3 is to use the update expression that we just talked about in order to generate the x superscript parentheses superscript 1. So this is the exact same expression. What we have is the new value of x will be equal to the old value of x minus the update coefficient times the gradient. Again, this tells us the direction in which we should be moving, and this tells us the length of the step or the length of the stride. And so here we see x parentheses superscript 1 bracket superscript 2. So this is the x variable for the first iteration, element number 2. Same thing up here, x parentheses superscript 1, so this is the first iteration, and bracket superscript 1, this is the first element. Note that the first iteration is after the 0th iteration using our notation. Next, step number 4, we check for convergence. We've talked about convergence several times during these AI modules. As such, I'm not going to discuss the topic in detail here. Essentially, we stop iterations of gradient descent once the value yielded by the objective function falls below a user-defined threshold for multiple iterations, or falls below a user-defined threshold consistently. So we can evaluate the optimality of our new value, of our updated x1 value, by plugging it into the objective function, and we see that it yields a value of 5.6931. So this is probably not the best we can do, and essentially we would continue iterating, going back to step number 2, until we received or saw a very small value here generated by the objective function. So we would continue looping until convergence. This slide shows the MATLAB script I used to continue the gradient descent implementation from the last, specifically to perform 15 iterations. Now I'm not going to talk about the code in depth. If you're interested, you can download it using the link in the top right hand corner. I do want to focus on this graph, which has 3 lines. The first of which in red is x1. It shows how x1 evolves from its initial value of -1. It evolves with the iteration number to its final value of about -0.25. We see that x2, as shown in blue, evolves from its initial condition of 0.1 to its final value a little bit less than +0.5, and the third line, shown in yellow, is the magnitude of the gradient. So we can see that the magnitude of the gradient starts off as pretty large and then settles to a near 0 value a little bit after convergence. And this makes sense because we know that when we've reached our minimum value, when we've reached our optimum, we expect that to be a critical point, to be a stationary point, at which the magnitude of the tangent of the gradient should be pretty close to 0. Before we end this module, I did want to ask one more question. We saw previously that a nonlinear function can present multiple maxima, multiple minima, only one of which can be the global value. So, when multiple local optima exist, how can gradient descent be guided toward the most favorable solution, or potentially the global optima? Now this is a pretty complex question, and assuming we don't employ variations on gradient descent like a genetic algorithm, this is primarily done by choosing good initial conditions. So the next logical question is, well, how do we define a good initial condition? What does that mean? And to answer that question, we need to discuss regions of attraction. For nonlinear optimization, the region of attraction for a given solution is the set of initial conditions that converge to its corresponding optima under gradient descent. Different solutions may have their own regions of attraction, separated by boundaries in the search space. So if we look to the right here, we can see a one-dimensional example, an optimization with respect to a single variable. The search space is shown on the x-axis. It ranges between -5 and +5. These yellow lines show the boundaries between the regions of attraction, which are colored red, blue, and green. The white line is merely the objective function. It demonstrates how the objective function changes with the x value within the search space. So the next question we may ask is, why are there 3 regions of attraction? In order to answer that, we need to look at the critical points or the stationary points on this graph. We have a maximum, we have an inflection point, and we have a minimum. All 3 present a point at which the gradient will be equal to 0. Generally, the boundaries between regions of attraction are associated with these critical points, with these stationary points, or asymptotes, or other regions for which the function is undefined. So why isn't there a boundary associated with the minimum? We'll talk about that in a sec, and we'll draw a temporary boundary for right now. The maximum, if we're talking about gradient descent, if we're talking about minimization, is an unstable critical point. And the reason for that is if we place an initial condition slightly to the right of it, gradient descent will guide it downward to the right. If we place a point to the left, it'll guide it downward to the left, right? Only if we place the initial condition directly on the boundary will it stay still, will it stay stationary. The inflection point is what we call semi-stable, a semi-stable critical point. And the reason for that is if we place an initial condition to the left, right, gradient descent will push it back to the inflection point. But if we place it to the right, it'll push it downward to the minimum. The minimum, again, if we're talking about a minimization problem, if we're talking about gradient descent, is a stable critical point. It's a stable solution. And the reason for that is because if we put an initial condition to the left, it guides it downward. If we put an initial condition to the right, it guides it downward to the local minimum. And essentially, any small perturbation from this minimum only causes gradient descent to push it back down to that minimum value. And so we see that boundaries between regions of attraction are associated only with unstable or semi-stable critical points. There's no need for a boundary here associated with the minimum because on either side of that minimum, gradient descent pushes it back to the same point. So in a very practical sense, the region of attraction associated with the solution is the entire region within which an initial condition will be directed by gradient descent to that solution. So, to find a global optimum, one must define an initial condition that falls within its region of attraction. Otherwise, the method may yield a suboptimal solution or diverge altogether, yielding no solution. The key takeaway here is that for nonlinear functions, gradient descent does not guarantee that a global optimum is yielded. Success, if we classify success as finding the global optimum, is heavily dependent on where we begin our gradient descent, where we set our initial condition. So again, I'm trying to be consistent here with homeworks. I want to assign another one. The solution will be posted after there's 10 attempts at solving it, 10 responses in the comments. I want you to consider the objective function below in terms of two variables, x1 and x2. So the objective function is equal to e to the 1 minus x1 plus 3x1 squared, so on. And so what I'd ask you to do is calculate the gradient of this objective function with respect to both input variables, then use that gradient to perform a single iteration of gradient descent by hand, yielding an updated set of x values, x superscript parentheses 1. I want you to employ an update coefficient of alpha equals 0.1 and an initial condition where both of the values are equal to 0. So you see here x superscript parentheses 0 bracket 1 and then bracket 2, right, both of those would be equal to 0. And then answer the question, does the objective function, the value that it yields, increase or decrease between those two iterations when you're feeding it x superscript 0 versus x superscript 1? And then finally, I want you to employ MATLAB, or you could also use Octave Online. You can Google that. It's a really great free MATLAB alternative to graph a convergence solution similar to the graph that we showed 2 or 3 slides back. So in summary, this module presents a review of gradient descent as applied to optimization of a highly or more nonlinear function. I invite you to watch the next module to see how knowledge of gradient descent leads into our discussion of backpropagation for supervised machine learning.